this video, you're going to learn how to do partial fraction decomposition, and we're going to go through the different types that you're going to want to know. This is designed to be a complete guide. I'm going to show you how to set up these problems, how to solve for the partial fractions, and we're going to go through two different key methods that are helpful to use. So let's dive into this video. You're going to learn how to do this as we go through. The first thing that you want to do is, when you're dealing with this large fraction, is you want to factor the denominator as much as possible. So what I want to do is I want to just show you the setup first, and then I'm going to show you how to solve for the partial fractions. So here I've already taken the liberty of factoring this denominator, and what you'll notice is that these factors, or these groups, they're all to the first power. See, 2x to the first, x to the first, x to the first. These are referred to as linear factors, okay, just like a line, like a first degree equation. And so what we're going to do is we're going to break these down into some smaller fractions that, when they're added back together, would give you back this fraction here. So the way you do this is you look at these factors in the denominator, and you're going to make each one of these fractions have one of the factors. So you're going to say 2x plus 1, we're going to say x minus 1, and we're going to say x plus 2. Now, because these are to the first degree, we want the numerator to be 1 degree lower. So that means that these are going to be to the 0th degree, or you could just, like a constant. So in this case, this is going to be a, this is 1 degree lower b, this is 1 degree lower c. Now, the key to partial fraction decomposition and the bulk of the work is solving for a, b, and c. Once you find out what a, b, and c are, if you want, you could go ahead and get a common denominator, combine these back together, and you would get back this original fraction, okay? But the idea is that as you go on in math, like into calculus, it's easier to work with these smaller fractions, and so that's what we're doing, is we're kind of working backwards and breaking it down. So let's look at the second type here. So this is called linear factors. Now this one here, again, I've taken the liberty of factoring the denominator. If it's not factored, you want to do that step first. Factor it as much as you can, and then look at the factors. Now again, you can see this is to the first degree, and this is also to the first degree. But see how this is x minus 3 squared? Or if you have x minus 3 cubed, or x minus 3 to the 4th, what you have is a linear factor, okay, that's been repeated. They call it a repeated linear factor. So the way you handle this is, when you go to write your partial fractions, is you say, okay, this is x minus 3, and I'm going to include x minus 3 squared. If it was x minus 3 cubed, I would have another factor, x minus 3 cubed. If it was to the 4th, I would have a fourth one, x minus 3 to the 4th. And the reason being is that when you go to add these together, we don't really know if there's just an x minus 3 squared fraction, or if there's both an x minus 3 and an x minus 3 squared fraction, because when we combine these together, it's still going to have this common denominator. So we have to consider, you know, the possibility that there could be these two groups here. Okay, so again, now we're going to look at the numerator, and you want the numerator to be 1 degree lower than the denominator. So this is a linear factor. This is x to the first. This is just going to be 1 degree lower, a constant. Same thing here. You want to look at what's inside. This is linear. You want to make this 1 degree lower. That's going to be a constant. Now, sometimes students make a mistake, and I made this mistake too when I first learned this, is I said, well, isn't this squared? Shouldn't this be like a to the first degree, like a linear factor? And when you do this, you just want to look at what's inside here in the parentheses and make it 1 degree lower than that, not the overall quantity here. Over here, same thing, linear, so we want it 1 degree lower. Now notice what I'm doing is, I'm not saying A or B. I'm picking a different variable, okay, each time to represent this constant. And the idea is that you could make this B and this A, or vice versa, but you don't want to repeat that quantity, because we're trying to figure out what these numerators are. So you want to make sure you make that a different variable. Now let's look at another example. Now number 3, we've got a quadratic factor, okay, because see, this is x squared. Same thing here, this is x squared. And I really can't factor x squared plus 3 further. So that's as far as we can go. So when I write our partial fractions here, I'm going to take this factor or group, and I want the numerator to be 1 degree lower. So since this is quadratic, or second degree, I need to make this ax plus b. Now what happens if this was a cubic factor, like x cubed? Okay, then I would make this ax squared plus bx plus c. What would happen if this was x to the 4th? Ax cubed plus bx squared plus cx plus d. So you want to go in, you know, descending order until you get down to that constant, but again, making sure that it's 1 degree lower. Now we also want to look at the possibility of this fraction here, okay, x squared plus 5, and that numerator would be cx plus d. Notice I'm not repeating into the variables a, b, c, d. I'm making sure that these are different so that when I solve for them, I know what numerator that quantity is going to go into. So again, you can have as many factors as you want, really. It just depends on how this factors. So you might have another factor, another one. There might be numerous fractions that we're breaking this down into, but then the bulk of this process is finding out what the a, b, c, and d are. And we're going to talk about that in just a minute, but let's talk about the different setups first. So hang with me. So for number 4, now notice we have here, we've got a quadratic factor that's been repeated. Okay, see how there's multiples here? This is cubic. So what we're going to do when we write this is we're going to consider all the different cases here. We've got x squared plus 1. We've got x squared plus 1 squared. And we have to consider x squared plus 1 to the third. So the idea is when we combine these fractions together, what's the common denominator? Well, it's still going to be x squared plus 1 to the third power, okay? But we have to consider that these denominators could have been to the first, second, or third. Again, if this was to the 4th power, I'd have another fraction here to the 4th. So this is called a repeated quadratic. Now again, remember the numerator, it's always 1 degree lower. So this is going to be ax plus b, cx plus d, ex plus f. And again, don't make the mistake of saying, oh, Mario, this is to the 4th power. Shouldn't this be cx cubed plus dx squared plus ex plus f? You just look at what's inside of the group here, inside of the parentheses. So when it's repeated like that, just look at this quantity. If it's a 2nd degree, make this linear. If it was a 3rd degree, then you make this ax squared plus bx plus c, like a quadratic, and go down to the constant. Okay, last type, and this is one that sometimes tricks students, it's called improper fractions. When the numerator's degree is the same as the denominator's degree or higher, that's considered improper. Remember how we always want this to be 1 degree lower? So if this is a tie, or this numerator is higher than the denominator's highest power, that's considered improper. And what you do is you do long division, okay? So let me just make an example, like say if I said 21 over 6. We all know that this is an improper fraction because the numerator is larger than the denominator. So what do? We say, how many times does 6 go into 21? It goes in there, let's see, what is that? That's 3 times, okay, with 3 left over. What do we do with the 3 left over? We take that remainder and we put it over the divisor, okay? But with partial fractions, you take this part right here, okay, this fraction, and you do the partial fraction decomposition on that. And we're going to talk about all these different examples, but just to show you, for this one, you would set up x squared minus 2x plus 3 is going into the numerator, x squared plus 3x. However many times it goes in, if there's a remainder, you're going to take that remainder over the divisor, and you're going to do the partial fraction decomposition on that. So let me erase the whiteboard. Let's get real here. Let's dive into each of the different types, and let's solve for these a, b, and c quantities, and I'll show you how this works a little bit more deep. Okay, so for number 6, we've got x plus 2 over x squared minus x minus 12. First step is you want to factor the denominator as much as you can. So when we factor this, what two numbers multiply to negative 12, but add to negative 1? That's going to be negative 4 and positive 3. Now, if you need to review factoring, I've got a video talk about how to learn all the different types of factoring. You can check that out. But I assume at this point you know how to factor. So this is our denominator. Now what we're going to do is we're going to write our partial fractions. And I'm going to take each of these factors. Oops, I forgot the x here. Take each of these factors, and we're going to put them in the denominators. Okay, so x minus 4 and x plus 3. Now remember, these are linear factors. They're to the 1st power. The numerator is going to be 1 degree lower. That's going to be a constant. So I'm going to label this a and b. Okay. Now what we're going to do is we're going to solve for a and b. And the way that we do that is we're going to solve this rational equation. And I've got videos about solving rational equations, but the short story is that you're going to multiply through by the common denominator. Now you might be saying, Mario, what's the common denominator? It's always going to be this denominator here, this one that you factored originally. If you just multiply through everything by x minus 4, x plus 3, that clears the denominators, gets rid of those fractions, and it makes it easier to solve for a and b. So I'm just going to write over here x minus 4 times x plus 3. And now what we're going to do is we're multiplying it to the right and the left sides of the equation. So it's keeping it balanced. We're not doing anything strange here. When I go ahead and distribute to this fraction, you can see that x minus 4 and x plus 3 are going to cancel. This is like in the numerator, this is like in the denominator. So that's just going to leave us with the numerator, x plus 2. When I distribute this to this fraction here, x minus 4 in the denominator, x minus 4 in the numerator are going to cancel, and that's just going to be a times x plus 3. And then lastly, when we distribute it to this fraction, you can see the x plus 3's are going to cancel, leaving us with b times x minus 4. Okay, now we're going to talk about the two different types of ways of solving for the a and the b. The first type, some teachers refer to as using convenient values, or the zeros, or strategic values. They have all these different kind of ways of saying it. But just think about what would cancel out this term here. That's if x is equal to -3. You see how I'm putting in -3? But you want to make sure you put -3 in for all of these x values. So whether you want to call them strategic, or zeros, or convenient, whatever you want, we're going to maybe write that down just to remind us. We're putting -3 in for x, so that's going to make this -1. -3 plus 3 is 0 times a is 0. That cancels out that term. And over here, -3 minus 4 is -7 times b. Okay, so now all I have to do is divide both sides by -7, and I can see that b is coming out to 1/7. Now, let's go ahead and let x equal +4. Okay, so if I do that, that's going to make this 6. That's going to make this equal to 7 times a. And 4 minus 4 is 0. 0 times anything is 0. That cancels out that group or term. If I divide both sides by 7, you can see that a is equal to 6/7. Okay, now all we have to do is we need to put these values back in for a and b. Now, sometimes students mistakenly just stop right here and say, okay, well, I'm done. The reason you want to put them back in is because your classmate might have made this a and this b, or they might have called them c and d or something like that. So what you want to do is you want to rewrite it and you want to say, okay, and I like to write the entire equation. So x plus 2 over the x squared minus x minus 12 is equal to a, which is 6/7 over the x minus 4, plus b, which is 1/7 over the x plus 3. That's your answer. Now, some teachers are okay with you leaving it like this, but technically, this is what's considered a complex fraction. You have a fraction inside of another fraction. It's complex, right? So you've got a couple different options. One option is you could factor out a 1/7 like this. Okay, see how I factor that out? Now you don't have the complex fraction. That's one option. Some people like that. Another option is you can bring the 7 to the denominator. So this would look like this, like 6 times 7 times x minus 4 plus 1 times 7 times x plus, like this. You can basically see I'm multiplying the 7 to the denominator and the 1 to the numerator, but it's kind of just like bringing this denominator down. This is also equivalent. So a couple different ways to write the final result, showing your partial fractions. And again, if you want to have some fun or just prove it to yourself, go ahead and add these two fractions together by getting a common denominator, simplifying. You're going to get back this fraction. So you're proving to yourself that these are actually equal to the original fraction. It's just that you've broken it down into smaller components. Now, this was method number 1. Some teachers hate this method. Okay, some students hate this method. So here's another possibility. The other possibility is you can distribute this a and this b. Okay, so let me write this down here. We've got x plus 2 is equal to ax plus 3a, just draw a line here, plus bx minus 4b. Okay, now what you do is you collect like terms. So you see this ax and bx. I'm going to write this as a plus b times x. See how I factored the x out? Plus, I'm going to group these together, 3a minus 4b. Now, the reason I'm doing that is because we're going to make two equations. We're going to say, see this x term and this x term? The right and the left sides, they have to match, right? Otherwise, it's not an equation. It's not equal. So I'm just going to set the coefficients equal. I'm going to say a plus b is equal to 1, right? And then I'm going to take the constant equal to the constant. So I'm going to say 3a minus 4b is equal to 2. Now we can solve a system of equations, and you learned a lot of different techniques for doing that. Substitution, elimination, graphing, matrices, Kramer's rule, many different techniques, right? So let's just keep this simple. Let's go ahead and multiply this top equation by 4. So that's going to give us 4a plus 4b is equal to 4. Make sure you multiply the whole equation by 4. Then when I add these together, see how the b's cancel, and I get 7a equals 6. Divide by 7, a is equal to 6/7. If I put the 6/7 back in for a here, you can see that b is equal to 1/7. 1/7. And that's what we got back over here. So this technique is sometimes a little bit easier to work with when there's more variables. Like if you have a, b, c, d, e, f, g, you might want to just do a system of equations as opposed to maybe picking these strategic or convenient or zero values. But sometimes this method is quicker, so you can pick either one, you'll get the same answer. Let's look at another example. Okay, for this next example, let's take a look at breaking this down into its partial fractions. So the very first thing you want to do is you always want to look and make sure that the numerator's degree is lower than the denominator's degree. If it's a tie or the numerator's degree is higher than the denominator's degree, then it's an improper fraction and you want to do the process of long division first, and then you can break down that remainder over the divisor further. We'll talk about some of those examples coming up in just a little bit. But in this case, the degree here is lower than the degree here, so we checked for the fact that it's not an improper fraction. The next step is to factor the denominator as much as you can. And I can see that this is x minus 1 times x minus 1. That multiplies to 1, and the negative 1x and negative 1x adds up to the middle term, negative 2x. I could also write this as x minus 1, the quantity squared. So this is our denominator, and notice it's a linear factor that's been repeated. So we call it a repeated linear factor. And remember from at the very beginning, when you have a repeated linear factor, the way we're going to write this is our denominators are going to be x minus 1 and x minus 1 squared. If this was x minus 1 cubed, we'd have x minus 1 squared, x minus 1 cubed. If it was to the fourth, we'd have 4 of those fractions. Now the numerator, remember, since this is linear, it's always going to be 1 degree lower, so that's going to be a constant or a. Same thing here. This is linear. It's going to be 1 degree lower. That's going to be b. Now, don't make the mistake, like I said, that I made when I first learned this. And I said, well, that's x squared, so this should be like linear, bx plus c. You just want to look at what's inside of the parentheses. It's a linear factor that's been repeated. Now, the math, behind this, why this process works, you can look up online. It's a little bit more advanced, but this is the process of how to solve for your partial fractions. So now what I'm going to do is I'm going to multiply through by the common denominator. Remember, it's always going to be this denominator right here. So I'm going to multiply the entire equation by x minus 1 squared. You can think of that as over 1. As long as I do it to the left and right sides to each term, that's going to clear the denominators. It's going to keep the equation balanced. So when I distribute it to here, these are going to cancel, numerator and denominator. That's going to leave me with 4x plus 3. When I distribute it to here, one of the x minus 1s cancels one of these x minus 1s, leaving a times x minus 1. And when I distribute to here, these are going to cancel, just leaving us with b. Okay, now you've got two choices. You can use the convenient values, or you can do the system of equations, whichever one you prefer. Sometimes one's easier than another, given the situation. Here, let's let x equal 1. The reason I'm picking 1 is because that's going to make this 0. 0 times anything is 0, and we'll be able to solve for b. So 4 times 1 is 4, plus 3 is 7. We said this is 0, so we'd have b equals 7. That was pretty easy. Now here's where sometimes students get a little bit stuck. They say, well, what value can I put in so that I can cancel out the b and solve for a? Well, there really isn't one. So in this case, you could just pick any value. And then a convenient value sometimes is just a small number for x, like you could do 0, 1, 2, or negative 1, negative 2. I'm just going to pick x equals 0. So if I put 0 in here, that's going to be 0 plus 3, which is 3. 0 minus 1 is negative 1 times a is negative a, and plus b. Well, we already know that b is 7, so let me replace this with 7. If I subtract 7, that's going to give me negative 4. Divide by negative 1, and you can see that a is equal to positive 4. Okay, that's it. Now all we have to do is put those back in for a and b. So let's go ahead and write the entire equation, 4x plus 3 over x squared minus 2x plus 1. Again, remember the reason that we're doing this is because somebody might have made this a and this b, or they might have picked variables c and d, right? So you want to kind of write the actual fractions, okay? And this is 7 over x minus 1 squared. Now again, if you want to check your work, get a common denominator, combine these together, and you'll see that it equals this. So that's your final answer. Now, remember we said there's two different methods. We could also make a system of equations. Some students prefer this. I kind of prefer this myself, okay, if you're curious. I just kind of like the fact that it's, you know, you're not just putting in numbers, you're just kind of writing this as a system. So this would be ax minus a plus b. So then what we do is we say, okay, 4x must equal to ax, which means that a equals 4. That was pretty easy. And then over here we have negative a plus b, that's the constant, equals this constant. So negative a plus b is equal to 3. We can put 4 in for a, so that's negative 4 plus b equals 3. Add 4 to both sides. B equals 7. And see, did we get the same thing? Yep, a equals 4, b equals 7. You're going to get the same partial fractions. Let's take a look at another example. Okay, if you're starting to get the hang of this, go ahead and try this problem and pause the video, and of course we'll go through it together. So first step is to see if it's an improper fraction. Well, you can see this is squared, this is cubed. The numerator is a lower degree than the denominator, so it's not improper. Okay, so then we go to the next step, which is to factor the denominator as much as we can. Now, it's good to be good at factoring. This is a difference of 2 cubes, and we're going to factor this as a binomial times a trinomial. Again, if you need to review factoring, especially like sum and difference of cubes, I have videos on that you can look up. So now what we're going to do is we're going to write our partial fractions. We can't factor this further, by the way. You want to factor it as much as you can. We've got a linear factor, we have a quadratic factor. So our fractions are going to look like this: x minus 3 and x squared plus 3x plus 9. Numerator is going to be a. Remember, that's 1 degree lower. This one is going to be bx plus c. Again, see, it's a second degree, so this has to be a linear or first degree, so bx plus c. If it was cubic, bx squared plus cx plus d, right? Okay, so now we have to solve for a, b, and c, and we do that by clearing the denominator, solving this rational equation by multiplying through by the common denominator. That's going to be this guy right here. So just visualize or write down that we're going to be multiplying by x minus 3 times x squared plus 3x plus 9. Remember, that's kind of like over 1. We're multiplying it to the left and right sides. We're keeping it balanced. We're basically clearing the denominators. Make sure you multiply it to each one of these fractions. Okay, so when we do that, these guys are going to cancel. We're going to be left with 3x squared plus 6x plus 9. Okay, here we're left with a. The x minus 3's are going to cancel, so we're going to have a times x squared plus 3x plus 9. And over here, the x squared plus 3x plus 9's are going to cancel, and we're going to have bx plus c times x minus 3. Okay, now you can do the strategic values, or the zeros, or the convenient values, whatever you want to call that method, where you're plugging in values for x. If you were doing that, 3 would be a good number, because that would cancel out this group and allow you to solve for a. 0 might be a good number as well. But on this one, I think I'm just going to make a system of equations. As it starts to get a little bit more complicated, I find it easier to do the system of equations method. And so to do that, we're going to multiply this out and collect like terms. So I'm just going to distribute the a. And so that comes out to, let's see, ax squared plus 3ax plus 9a. Okay, over here we have to distribute twice. So that comes out to bx squared plus, well, so bx squared minus 3bx plus cx minus 3c. Okay, now we're going to collect like terms. So, and this is equal to this right here. So 3x squared plus 6x plus 9. Ax squared plus bx squared. So let's write that as a plus b times x squared. Over here we've got the x terms, so we've got 3ax and negative 3bx and cx, so that's going to be, let's see, 3a minus 3b plus c times x. So basically you can see I'm just factoring the x out, okay? And then for the constant terms we've got 9a minus 3c. See how it gets kind of complicated, right? But when you write it like this, it's going to be easy to solve this system because we're just setting the x squared equal to the x squareds, and then the x's to the x's, and the constants to the constants. So that tells me that these coefficients must be equal. A plus b must equal 3. Okay, that's one equation. 3a minus 3b plus c is equal to 6. And 9a minus 3c is equal to 9. Okay, that's the system that we have to solve. Again, you can use any method that you want. I think what I'm going to do here is I'm going to eliminate the c's with the second and third equation. So I'm going to multiply this by 3, which is going to give us, let's see here, let's write it over here. This is going to give us 9a minus 9b plus 3c is equal to 18. And this equation, I'm just going to copy that down, 9a minus 3c equals 9. When we add these together, see how the c's cancel, we get 18a minus 9b equals 27. And I'm going to combine these two equations together to eliminate the a's or the b's. I think I'm going to eliminate the b. I'll multiply this equation by 9. So I multiply this equation by 9. That's going to give us 9a plus 9b equals 27. Okay, so then if I add those together, you can see we're getting 27a. Let's write it over here. 27a, the b's cancel, equals 54. Divide by 27, okay, a equals 2. That did take a little bit of work. Now if a is 2, plug it back in here, that means that b equals 1. Okay, that wasn't too bad. And now we've got a and b. Let's see, we can also put a 2 here. This would give us 18. So that'd be negative 3c. If I subtract the 18, that's negative 9. Okay, that means that c is equal to 3. Okay, so now if we rewrite our equations, our partial fractions, I mean, we've got a equals 2, so this is going to be 2 over x minus 3 plus 1x, or we could just say x, plus 3 over x squared plus 3x plus 9 is equal to this original fraction, 3x squared plus 6x plus 9 over x cubed minus 27. Okay, let's box that. And that's your final result. These are your two partial fractions. Again, you can check your work by getting a common denominator, combining these together, and you'll get back this original. So the whole idea when you get to calculus is that working with these two factors, or these two fractions, I mean, it's going to be a lot simpler. It's going to be a lot easier. It's equivalent, but we're just breaking it down to make some of the operations in calc a little bit easier. So let's erase the whiteboard. Let's do another example. Okay, what do you think for this one? See if you can pause the video and try this. Well, when I look at this, you can see the denominators already factored. So that kind of saves us a little bit of work. And you might think at first glance, you might say, Mario, isn't this degree the same as this degree? Isn't this like an improper fraction? Well, if you were to FOIL this out, this would actually give you x to the 4th power. So you can see that the numerator actually is a lower degree, so it's not improper. But it's good to check for that first. The next step would be to factor. This is already factored, and we want to look at our partial fractions. Now notice this is a repeated quadratic factor. We can't factor this any further. We can see it's that quadratic factor repeated. So when we write our partial fractions, they're going to look like this: x squared plus 3 to the 1st and x squared plus 3 to the 2nd. Now if this was to the 3rd, we'd have x squared plus 3 to the 3rd. So we're trying to consider, what were these fractions originally, okay, if we were to add them together to give us this original. We're trying to break it down. It's factoring, right? It's like decomposition. So the numerators, though, because this is quadratic, they have to be 1 degree lower. See, if this is x squared, this has to be ax plus b. If this was x cubed, ax squared plus bx plus c. Same thing here. This is going to be cx plus d. Again, make sure you make the variables different, and don't make the mistake of thinking, oh, this is x to the 4th, and make this cx cubed plus dx squared plus ex plus f. Just look at what's inside, make this 1 degree lower. Okay, good. So now we've got the setup. Now we have to just clear the denominators by multiplying through by the common denominator, which is always going to be this guy right here. So this is going to be x squared plus 3, the quantity squared. Now I'm going to distribute that to each one of these fractions. You're doing it to the left and right sides. They're keeping the equation balanced. We're just doing that to clear the denominators. If I distribute it to this fraction here, we're just going to be left with 2x squared plus 5x plus 5. With this one of the x squareds plus 3's cancels with this x squared plus 3, leaving us with ax plus b times x squared plus 3. These ones are going to cancel, just leaving us with cx plus d. Okay, we got a lot going on here. Now, you could do the method of picking values for x, but this looks pretty complicated to me, so I think I'm just going to do the system of equations. So I'm going to FOIL this out, And we're going to group the like terms together. So I'm just going to distribute. This gives us ax cubed plus 3ax plus bx squared. Just have to be really careful with the arithmetic. Plus 3b, erase that, plus 3b, plus cx plus d. Okay, now we're setting it equal to this side here. So we're going to look at the like terms. So we've got ax cubed. There's no x cubes over here. So this is kind of like 0x cubed, right? So that means that a is equal to 0. All right, so we already solved for a. That's good news. Now let's look at the x squared. So we just have this x squared term here. So that's equal to this x squared term. So that means that b equals 2. Okay, this is looking good. And now let's see, for the x terms, we've got 3ax and cx. So we've got 3a plus c. Notice I'm just using the coefficients. I'm not using the x's. Is equal to the coefficient in front of the x term here. That's equal to 5. But we know if a equals 0, 3 times 0 is 0. So that tells us that c is equal to 5. Okay, that's great. And then the constants, 3b plus d, is equal to the constant here on the left side, which is equal to 5. We already know that b is 2, so that's going to be 3 times 2 is 6, plus d equals 5. Subtract 6. That means that d is equal to -1. That was pretty easy, right? So now let's put it back in. Now if a is 0, don't worry about it being 0. 0 times x is just going to be 0. So that's going to be 2 over x squared plus 3. C is 5, so that's going to be 5x plus d, which is -1, or I could just write this as 5x minus 1, over x squared plus 3 squared. Those are our partial fractions. Now I'd like to set it equal to the original, so that's 2x squared plus 5x plus 5 over x squared plus 3 squared. Make sure we got that right. Okay, perfect. So that's your partial fraction decomposition. Now again, if you want to check your work, get common denominators. You can combine these together and you'll see that it equals the original. Again, this is a little bit easier to work with and you got it. So let me erase the whiteboard. Let's look at the next example. Okay, let's look at number 10 now. So for number 10, we've got x squared plus 1 over x squared plus 3x plus 2. So what do you think about this one? Try and do this one. What you'll notice here is that the numerator's degree is the same as the denominator's degree. So what that tells us is that this is actually an improper fraction. So our first step, our very first step, is to rewrite this by doing long division. Okay, so I'm going to take the denominator, which is x squared plus 3x plus 2. I'm going to see how many times it goes into x squared plus 1. Now x squared plus 0x plus 1 is the same as x squared plus 1. I'm just kind of putting a placeholder there. So what times x squared is x squared? That's just going to be 1. So if I distribute the 1, I get x squared plus 3x plus 2. You can look up videos on my channel about long division if you need help with this. And then you're subtracting, or what some students like to do is change the signs to the opposite and add. So this comes out to -3x minus 1. Now notice this is to the first degree, this is to the second degree. When this degree is lower, that's our remainder. And what we do is we put our remainder over our divisor. Now what we're going to do is we're going to do the partial fraction decomposition on this part right here. Okay, we're going to ignore the 1 for just a moment. Now the first step is to factor the denominator, right? So this is x plus 2 and x plus 1. So when we write our partial fractions, let's go over here. This is -3x minus 1 over x plus 2, x plus 1. What kind of factors are these? They're linear factors. They're to the first degree. So this is going to be x plus 2 and x plus 1. We want the numerator to be 1 degree lower. That's going to be a constant. So a and b. Okay, a and b. And now all we have to do is solve for a and b. Now we're going to clear the denominators by multiplying through by our common denominator. That's the x plus 2, x plus 1. When I distribute it to here, that's going to cancel numerator and denominator, leaving us with -3x minus 1. When I distribute to here, the x plus 2's cancel, leaving us with a times x plus 1. When we distribute to here, the x plus 1's cancel, leaving us with b times x plus 2. Now this one is going to be really easy to do the strategic values, right? So we could just say let x equal -1. That's going to make this 0, right? This is going to come out to 3 minus 1, which is 2. And this is going to be negative 1 plus 2 is 1 times b is b. So we solve for b. That was pretty quick. We can also say let x equal negative 2. That's going to cancel out this term because negative 2 plus 2 is 0. That's going to give us 6 minus 1, which is 5, equals negative 1 times a. Divide by negative 1, so a is negative 5. Okay, that was pretty quick. And so now when we write our partial fractions, here's where students sometimes make a little mistake. We have to include this 1 over here. So it's going to be 1 plus, okay, a, which is negative 5, over x plus 2, plus b, which is 2, over x plus 1. Now you could write this as minus positive 5 over x plus 2. You could even change the order of these fractions, okay, because addition is commutative. But if you were to get a common denominator, equals the original here, which is x squared plus 1 over x squared plus 3x plus 2. But again, if you get a common denominator for this group, and this group, combine them together, you're going to get back that original fraction. So let's take a look at one other example. See if you can do this last example on your own, and we'll go through it together. Okay, what do you think for number 11? Well, I noticed right away that the numerator's degree is higher than the denominator's degree. That tells us this is an improper fraction. So the first thing that you want to do is you want to do the long division and rewrite this, and then we'll see if we can do the partial fraction decomposition further. So let's set up our long division here. So this is going to be how many times does x squared plus 3x minus 4 go into the numerator? 2x cubed plus 7x squared minus 2x plus 18. By the way, if you're in pre-calculus studying partial fraction decomposition, you might want to become a member at the additional videos level. I've got some pre-calculus midterm and final exam reviews on there that can help you prepare for your final or your midterm. So check that out. Join as a member. That would definitely be a good resource for you. But now for here, we want to say how many times does x squared go into 2x cubed? That's going to be 2x times, right? So I'm going to put 2x here. I'm going to distribute. This gives us 2x cubed plus 6x squared minus 8x. Make sure you distribute to all of those terms. Now we're going to subtract, but remember subtraction's like adding the opposite. So this comes out to x squared plus 6x plus 18. How many times does x squared go into x squared? That's 1 time. So if I distribute the 1, I get x squared plus 3x minus 4. And if we subtract, which is like changing the sign to the opposite, and adding, now notice this is the 1 degree lower than this. See, this is x to the first, this is x squared. This is our remainder. And what do we do with the remainder? We put the remainder over the divisor, x squared plus 3x minus 4. We're going to do the partial fraction decomposition on that fraction right here. So the key is, remember, to factor the denominator as much as you can. And let's bring it over here. So this is 3x plus 22 over x plus 4 times x minus 1. Okay, these are linear factors. Let's just do our partial fraction decomposition. Remember, the degree in the numerator is 1 lower. This is going to be a constant. Same thing here, 1 degree lower. We're going to clear the denominator by multiplying through by x plus 4x minus 1. That's the common denominator. To clear the denominators, if we distribute, we're going to get 3x plus 22. These guys are going to cancel. Over here, we're going to get a times x minus 1 and b times x plus 4. Now, we're going to pick strategic values. I think that's going to be the quickest way here. We're going to say let x equal 1 to make this term 0. So that's going to give us 25 equals 5b. Divide by 5, so b is equal to 5. Okay, that worked out nicely. And if we let x equal negative 4, that's going to zero out this term. That's going to be negative 12 plus 22, which is 10, equals negative 5a. So a is equal to negative 2. Now all we have to do is put this back together. But again, sometimes students forget this portion right here. This is part of our partial fraction decomposition. So this is going to come out to a. Now in this case, see, a is negative, so I'm just going to make this a minus. I'm going to say minus 2 over x plus 4. plus b was 5, so 5 over x minus 1. Again, this is equal to the original. I'm just going to draw an arrow here, okay, for simplicity. And that's your partial fraction decomposition. If you were to get a common denominator for all these fractions, combine them together, you're going to get back the original. Great job if you're able to follow all these examples. If you want more practice, you want to do some on your own, and you want to be able to check, did I do it right, or where am I going wrong? Check out a video I did previously right there on partial fraction decomposition. It's got almost over 1 million views now. I put it up a few years ago, and a lot of students have benefited from that. So go over to that video if you want more practice and do some problems on your own. I look forward to seeing my other videos. I'll talk to you soon.